Hello everyone, welcome back to Altium Academy. I'm your host, Zach Peterson, and today we're going to be talking about AC coupling capacitors on high-speed interconnects and specifically on transmission lines transmitting high gigabit per second serial data streams. Now this topic came across my radar because, of course, a post came across my LinkedIn feed and I got to see some great comments from all of you fine folks out there watching this video. So we're going to look at some of those comments. We're going to look at what the experts say about this. Let's go ahead and get started. So the topic of this video is AC coupling capacitors and where you should use them on differential transmission lines, specifically on interfaces that are providing high gigabit per second serial data streams. Now, this all came about because I saw this post on my LinkedIn feed from Darvin Ranjith. This post is all about placement of coupling caps on TX and RX lines for an SGMII interface. And he's asking, which one of these is correct? Should these capacitors be placed close to the transmit side or close to the receive side? And then here you can see in option 1 and option 2 that you have them placed not just close to the transmit and receive, both on the FPGA side, but also on the PHY side. Now there are some variations of this. Sometimes you'll see them both placed on the transmitter on both ends, or both placed on the receiver on both ends, and you'll have nothing placed close to the transmitter. So there are a few variations of this if you start to look on the internet. And in particular, this image was actually taken from a Stack Exchange post that's basically asking about this whole design practice with AC coupling capacitors. So the question that Darvin asks here is, which one of these is correct? Now, my response got quite a few replies, and there were many other replies from other folks in my network who decided to chime in. First, Darvin Ranjith, the original poster himself, writes, transmission lines and capacitors are linear, but termination placement affects signal integrity. Isn't that kind of what I said, though? If they're both terminated to the same target impedance at both ends of the line, then it doesn't. But let's suppose that one side wasn't terminated, then it would affect the placement. Placing capacitors anywhere can disrupt impedance matching, leading to reflections, jitter, and signal degradation. Of course, no source was cited here, but that's okay. Javier Galnares writes, Darvin Ranjith, I disagree. Placing a capacitor divides a transmission line into two stubs no matter where the capacitor is placed. I think you are mixing the concepts of skew and jitter if transmission line lengths are mismatched. Now, this is a common disagreement. If you start to look into this topic, you'll see a lot of people who say they need to be placed in one of the two locations, and then other people will state that it doesn't really matter where you place them. We see this in some of the other replies to this post. Darvin also writes, Javier, you're absolutely right that an AC coupling capacitor divides the transmission line into two segments. However, placement does impact signal integrity due to impedance matching. If the receiver has built-in termination, placing the capacitor too close to it can disrupt the impedance continuity. And then he says, quiz, this is exactly why checking the datasheet for termination details is critical. Many engineers ignore internal determination when placing AC coupling capacitors. And then he provides a datasheet from Texas Instruments. Now, there was a reply to this comment with the datasheet link. It is not my intention to turn this discussion into a scientific project, but the datasheet you attached does not say anything about the location of AC coupling caps. They have very detailed section related to the PCB, and there is no mention of the location of the AC coupling capacitors. This implies that the location is not important with respect to TX or RX ends. Now, I pulled up that data sheet and you can see the SGMII layout guidelines section right here. And if you just read through this list that I have on screen, very clearly you can see that they do provide a lot of details as to the size of the capacitors, which package the size they should be, what the traces should be routed to in terms of length matching and differential impedance, but nothing about the placement or the location of those capacitors. Very interesting. It's almost as if the placement doesn't really matter. Let's look at another comment on this post. Hamal Shevli writes, if you use series termination, it's better to put the caps near the source, and when using parallel termination, which would be at the load, it's better to put the AC coupling caps near the load. He talks more about it in this blog post. Now, I actually read that blog post, and that blog post is not about AC coupling caps at all, so I don't know if that was a mistake or something, but he doesn't really talk about it in this blog post. Anyways, there's still this disagreement now relating to whether you terminate at the source or at the load end. Let's look at another comment. Hamad Naeem writes, they should be placed at the TX side for both scenarios for the simple reason of stopping the spread of the DC offset as the signal moves and letting the clean signal go through. Ali Uzel writes, it depends. If the connection is on the same PCB and direct between the two components without going through any connector, then it does not matter. If there's a connector, the caps should be placed near the connector on the TX plus or minus differential pair for the chip located on the daughter board. Caps for the other side can be placed close to the transmit differential pins. Interesting. Now, this is a good point because some interfaces do have to traverse over a connector. Perfect example is PCIe, and those interfaces do make use of AC coupling capacitors. So this brings up another wrinkle. Do you put them on the load side of the connector or on the driver side of the connector? The last reply we're going to look at on this post comes from Christian Andre D'Souza. He writes, I agree with Zach Peterson, but here are the details that are implicit to his comments. Number one, the edge rates of the signals will always be higher or faster at the transmitter pins, and that is true. Since impedance is frequency dependent, the impedance discontinuity will be more significant in the case of improperly tuned AC cap layout structures at the transmitter rather than the receiver. I think that's also true. As long as the AC caps are transparent to the signal launch, then the placement is irrelevant. Exactly, I think that's also true. So naturally, the concerns above are not that critical for SGMII, which is only running at about 1.25 gigabits per second, which would not be the case in some much higher data rate multi-gigabit per second signaling. These are all really great points, and he's actually saying something that jives with one of my comments in the original reply that I showed on screen, and that is the impedance matching has to be very precise within the required channel bandwidth. As you go up to a higher data rate, you're then going to extend that required channel bandwidth up to higher frequencies, and that means your impedance match has to be better up to even higher frequencies, at least up to the channel bandwidth limit, ideally exceeding the channel bandwidth limit. Of course, folks who are familiar with parasitics will know that any parasitics in the load or the source or along the line can create an impedance deviation within the channel bandwidth. Those parasitics include pin package inductance, the parasitic capacitance and inductance of the pads in your coupling capacitor footprint, or the load capacitance or the pin inductance at the load end. If those parasitics are too large, then they will create an impedance deviation within the channel bandwidth, and then you will have an issue with non-reciprocality along that channel due to the placement of that coupling capacitor. Now, even if you start searching online, you're going to find conflicting information. I even went on Google and I just looked up AC coupling capacitor location. And you can see here that Google's AI overview tells you that the AC coupling capacitor is typically placed near the receiving end of a signal path, usually close to the input pin of the receiving circuit or integrated circuit. Now, it then notes in the very same sentence, in high-speed data rate interfaces like PCIe, they are often positioned near both the transmitter and receiver ends of the differential pair with specific placement depending on the interface standard and circuit design. So it seems that we have three options, as I noted at the start of the video. Place them always near the receive end, place them always near the transmit end, or it doesn't really matter where you place them. Now, on this topic of AC coupling capacitors, of course, the placement is the most contentious issue, but there are other design points that have to be considered. One of those is, for example, how much capacitance do you need? It's usually 10 nanofarads or 100 nanofarads that's recommended in data sheets. Another question is, how big should the package be? Should you use an 0603, 0402, or 0201 package? Another important question, will the results be different if you're doing striplines or microstrips? And last but not least, one point that often gets overlooked is the use of a cutout in the ground plane below an AC coupling capacitor. Should you include the cutout or should you keep solid ground? I decided to do a little bit of research on this. I located some simulation data and test data, and let's go ahead and dive in and see if we can resolve some of these design issues around AC coupling caps. Now, the first thing I want to bring up around AC coupling caps is that sometimes you actually don't need them even though they are present on the interface. Take a look here at this example in Altium Designer. This is a part of the schematic from our Ethernet switch project, and in that Ethernet switch we have a connector for a fiber optic transceiver. So this SFP connector is located here in this sheet, and you can see here that we have our TX and RX lines routing into this connector. Now, these 0 ohm resistors that you have here on these lines could be used to place AC coupling capacitors. Now, in the board that we built, we just left them as 0 ohm resistors, but like I said, you could place coupling capacitors here. Now, the reason we don't have to place the AC coupling capacitors here at these locations on these lines is because under the standard that defines optical fiber transceivers and SFP connectors, the fiber transceiver already contains AC coupling capacitors built into the module. So again, read those data sheets because the coupling capacitors might already be built in somewhere in that interface. Now, if you start looking to the semiconductor manufacturers for guidance, you might see some incomplete or somewhat contradictory guidance. Here I have a web page from Intel on screen where they're detailing the location of AC coupling capacitor placement. And you can see here that they are recommending the use of 0402 or 0201 package size capacitors. The other thing that they're doing is to recommend a cutout, as you can see here in this graphic. Now, they're also routing from a top layer trace pair to an inner layer trace pair, so you can see that they have vias placed on this interconnect, and those vias are placed in pad. Now, as far as the location is concerned, they're recommending to place it at the device end. I'm reading that as the receive end, or at the connector end. So this would be for like a PCIe edge connector. They're saying do not place them in the middle of the trace routing. That's very interesting because if you place those caps close to the connector, they are essentially in the middle of the trace routing, but we'll leave that alone for now. Let's see what Texas Instruments has to say. Texas Instruments has a pretty good guide here on AC coupling between LFE, PECL, LVDS, and some other logic standards. And you can see here in these graphics that they're essentially telling you to place the AC coupling caps at the receive end of these links. So they're saying the same thing. However, if you just Control F your way through this data sheet and try to find anything related to a cutout, they don't say anything. There's no mention of a cutout at all in this data sheet. So again, some incomplete guidance here from Texas Instruments. Now let's see what some SI experts have to say about this topic. Here I'm on sigcon.com, and you should all know this is Dr. Howard Johnson's website, and here he has a page specifically about DC blocking capacitors. As we scroll down here, we're going to see that he gives us two different motivations for installing the AC coupling caps near the transmitter or near the receiver. Now you can see here in this paragraph, he states, as with any reflection, if it occurs within much less than half a baud interval of either the source or the load, the reflections generated by each data edge will generally fall somewhere within that same baud interval. This principle motivates the idea that the DC blocking capacitors should be installed close to the transmitter. Essentially, he's acknowledging that if you have an impedance discontinuity within the required channel bandwidth, it is likely to stay near the transmit side of that link rather than extend out to the receive side. And so that motivates placing those coupling capacitors closer to the transmitter. Now let's see what Dr. Johnson has to say about placement at the receive side. If you scroll down, you'll see here there is a paragraph about placement at the receive end, and one of the issues that he brings up in this paragraph is with hot pluggable modules. And of course, fiber optic transceiver modules like the one that we showed for the Ethernet switch project, those modules are hot pluggable. Now in this case, with hot pluggable modules, he's arguing for placement of the DC blocking capacitors near the receiver rather than the transmitter. Now, one thing you can see here in this previous paragraph, he notes, in many cases, the DC blocking capacitor must have a hole cleared in the reference plane underneath the component to relieve the excessive capacitance underneath the body of the component. All other traces must be kept clear of this region. So this is interesting. We have an SI expert acknowledging that there are two different places in different situations where you could certainly justify putting the AC caps always near the transmitter or always near the receiver. Let's take a look at some test data to see if we can see a real difference between placement at drive side or receive side. Here I'm on everexceed.com, and I've never heard of EverExceed, but they do have a page here on their website where they're looking at the role of AC coupling capacitors in high-speed interconnects. And you can see here that they define two situations, and then they provide some test data for these situations. Here they have an example where they're driving at port 1, and then they have caps placed close to port 2, which would be the receive port. And then they have the opposite. They're driving at port 1, they place the caps close to port 1, and then they receive at port 2. Let's take a look at their test eye diagram. Here you can see on their first eye diagram, it looks pretty open. There's just a little bit of degradation right here leading up to the high voltage level, but you can see here that it is pretty much an open eye. So it doesn't appear to have major degradation from placement close to the driving port. What about when it's placed close to the receive port? Well, the eye does look a little bit more open. We don't see anything with jitter, apparently, when we compare these two eye diagrams, but we do see a little bit of degradation in the amplitude. So they're concluding that placement near the receive side is also a better option. Now, in another test, they compare a small capacitor versus a large capacitor. So here, they're using a 0.1 microfarad capacitor. But then when they take that capacitor and make it very large, make it a 10 microfarad capacitor, you can see a very significant degradation in the eye diagram. You can see eye closure, and it looks like we have a little bit more jitter in the rising edge in this eye diagram. So clearly a smaller capacitor is probably going to be better. Next, let's take a look at some work by Yuri Shlepnev, who you should all know is one of our frequent podcast guests, as well as founder of Simberian. Here on screen, I have one of his app notes dealing with modeling and simulation of differential links with AC coupling capacitors. And as we scroll down here, we're going to see some simulation data that compares the use of a cutout without a cutout, as well as package sizes. Here in this simulation model that he's building, he sets up a 0402 capacitor close to the RX port, since that is the conventional wisdom. And then you can see here some simulation results when the model includes a cutout and omits a cutout below the coupling capacitor. Now you can see here in this S parameter plot that we have a pretty dramatic difference in the channel performance when we include the cutout versus when we omit the cutout. Here you see almost a 20 dB improvement in return loss when the cutout is included below a 0402 capacitor. Now what about a 0603 capacitor? Well, here on the next slide, we also see an improvement with the cutout below the capacitor. However, in general, all of the data is worse when we use a larger 0603 capacitor. Now, this is consistent with some of the data that we saw from some of the other resources in this video. What looks like to be more important is not necessarily the placement at the RX or the TX end, but it's actually much more important to have that ground cutout below that AC capacitor. It also appears that physically smaller capacitors in terms of the package size, as well as smaller capacitance, are also better for signal integrity performance. So my conclusion here is this: worry less about the placement of the capacitors and more about the sizing of the capacitors, designing the capacitor footprint, and then placing that ground cutout below the capacitors. Now there's one question that we haven't answered yet. What about strip lines? Is everything different when we use strip lines instead of using microstrips? Well, let's hop onto the whiteboard and we can see what's different when we use strip lines with AC coupling capacitors. Now, I think the big takeaway from all of those resources that we saw on screen is that if you have an impedance mismatch within the required channel bandwidth, then it will start to matter where you place those AC coupling capacitors. However, if the impedance mismatch exists outside the channel bandwidth, then the location of the capacitor placement doesn't matter. Now, this becomes important when we start to look at strip lines versus microstrips because, of course, in order to route into a coupling capacitor, strip lines are going to need vias, and those vias could become an impedance discontinuity, including within the channel bandwidth that you're trying to route. Let's take a look at a typical channel model. Typical channel model would involve differential driver. We have our differential pair coming out to some vias. We then have our caps. We then have another pair of vias, and then this will come over to a receiver. Now, of course, what we care about here in this example is not just the placement of the capacitors, but whether or not these vias create an impedance discontinuity as the signal travels along this direction. So looking into the vias from this side, do we see an impedance discontinuity? First, have the vias been designed so that the via differential impedance, we'll just call this ZD via, is matched to the differential impedance of our traces? We'll call that ZD, question mark. So, do we have this condition? Well, these vias have to be intentionally designed so that you achieve this matching condition. And that means sizing the antipad and the spacing between those vias properly. Now, typically at channel bandwidths below about 3 gigahertz, these vias don't really matter. But when we're talking about high data rate serial interfaces, they're going to have a channel bandwidth requirement of much higher than 3 gigahertz, and so this condition does start to matter. So you have to design the vias such that they do achieve this impedance matching. But there's something else here that can happen with vias. For example, we can have stubs. Stubs are the extreme bandwidth limiting element on vias, particularly through-hole vias. So for example, if I have a channel bandwidth requirement, let's call it BW channel, of 10 gigahertz, and I use stubs, and the stubs have their first resonance at, let's say, 7 gigahertz, well, that's going to create an impedance mismatch within my channel bandwidth, and then the placement of these capacitors does start to matter. Now, of course, in the ideal case with placing these vias, we would just want to eliminate the stubs or make the stubs smaller, either through back drilling or just by using blind and buried vias. And so, of course, that would push this first via resonance from the stubs up to a very high frequency, and we essentially wouldn't notice it within the channel bandwidth. So this idea of eliminating stubs in order to eliminate an impedance mismatch that produces high losses along this interconnect is consistent with the other takeaway that we saw looking at microstrips. You have to eliminate those impedance mismatches within the channel bandwidth in order for the interface to work. And if you do that, as well as all the other design points correctly, the location of the placement of these coupling capacitors is going to be much less important. Thanks for watching this video, everybody. This is such an important concept if you're going to be doing any kind of routing of differential pairs specifically for high data rate interfaces. If you ever have any questions and comments, of course, leave them in the comments section. And if you ask a great question, it just might end up in one of these videos. And of course, if you make a great LinkedIn post, it also might end up in one of these videos. Make sure to hit that subscribe button, hit that like button, and don't forget to call your fabricator, folks. We'll see you next time.